Imagine that your job is to travel from city to city selling bricks. On your next expedition, you intend to visit 5 cities. However, all you know are the distances between all the cities, and your car has a limited amount of gas. So you need to find a route that isn't too long. Even for a computer, finding a valid path is harder than you might think. With only 5 or 10 cities to visit, you could find a solution in less than a second. But for 15, it could take hours of computation. And for 20 cities, a computer may need almost 2,000 years. Let's think about another situation. Imagine you have to pack for a trip, and all you can take is one suitcase. You have a pile of things that you would like to bring, each with its own size and weight. You need to pack a selection of items that fits in your suitcase and doesn't go over the airline's weight limit. Just like the first problem, if you give it enough items to check, a computer may take years to find a valid solution. Why does this keep happening? Aren't computers supposed to be good at this type of thing? To understand this, we need to learn how computer scientists think about efficiency. There are 2 main types of problems we can solve with a computer: polynomial and non-deterministic polynomial, or P and NP. Problems with polynomial complexity can be solved with algorithms that take as many steps as some polynomial function of the amount of data. If you have n items, it may take n steps, n squared, or even the logarithm of n. However, NP problems require many more operations. Like the brick selling or suitcase packing problems, we don't have a solution faster than just trying every combination until one works. Imagine trying to guess a 4-letter password that only uses the letters A and B. You'll have to go through a few options, but you'll find it eventually. But what if you could use all 26 letters, or add in numbers and special characters? NP problems get bigger and bigger very quickly. These algorithms would require a non-polynomial number of steps. For example, n to the nth power, or n factorial. The salesman and suitcase problems are also special for another reason. They're actually the same type of question. It's hard to find a good route or collection of items to bring, but it's really easy to check if a specific combination actually works. It doesn't take much time to add the size and weight of each item to see if it'll fit in your suitcase. NP problems like this, that seem hard to solve but easy to check, are called NP-complete. Computer scientists actually don't know how long it takes to solve an NP-complete problem. We just haven't found an efficient solution yet. And if you find an algorithm that can solve one NP-complete problem in polynomial time, that means it's possible to solve them all just as easily as we can check. This unknown is one of the Millennium Prize problems. 7 unproven math ideas that each come with $1 million to whomever solves it first. But if you manage to answer this question, 1 million may not be a big enough prize. NP-complete problems extend well beyond selling bricks and packing suitcases. Modern cryptography, like public key encryption, relies on secret keys that are very difficult to generate, but easy to check. Protein structure prediction, which is invaluable to medical research and drug development, can also be modeled as NP-complete. If it's possible to solve these problems quickly, all of computing would fundamentally change. And with it, many of the world's issues.